series of lectures to celebrate the 50 years of Turing Award. Turing Award is the most prestigious award which is given for significant contributions that are made in the field of computer science. So to celebrate that, this is actually 50 years since it started in 1966. So we have been organizing lectures. Already 2 lectures have been completed, one on Dijkstra and another on RSA. And this one is going to be the 3rd one. In connection to that, actually, we would like to play a video which has been prepared by the ACM headquarters. Some glimpses of ACM Turing winners and their contributions. Those will be in the video. Please watch that. After that, we will get to the main program. Yeah, thank you.
Long before many could envision the concept of computers, Mathematical saw the tremendous potential all himself. Each year, ACM honors outstanding contributions to computing with the presentation of his name. In the coming months, ACM will celebrate 50 years of the ACM AM Turing Award, as well as many of computing's greatest achievements. First, however, we'd like to show you why ACM chose to celebrate the memory and contributions of Alan Turing.
Alan Matheson Turing was a remarkable visionary who helped shape the diverse fields that would become computer science. In 1936, he launched the modern computer era with his classic paper on computable numbers. In it, he conceived his universal Turing machine, which he then proved could compute anything that was computable. During World War II, while working at Bletchley Park, he co-designed an electromechanical computing device, which his team of codebreakers used to help crack the Enigma codes used by Nazi Germany. In 1950, he developed the criterion now known as the Turing test to determine whether or not a machine could actually think. In 1966, the Association for Computing Machinery instituted the ACM-AM Turing Award. For half a century, Turing laureates have advanced all fields of computing science, many having emerged since the first presentation of the award.
Turing's role was the visionary. From the rudiments of computing at the time, he was able to extrapolate the immensity of what a, quote, computer, unquote, could do.
There is a new giant around, and that is computation. Computation is the glue that keeps the world together.
40-odd years after we did our original work on the Internet protocols, and the fact of the matter is people are still stuck at looking at screens and keyboards, and many people are 7/24 stuck to them.
An intelligent agent should be equally good for an illiterate person in a village. We should have 2 kinds of agents: cognition amplifiers, which do things we know how to do, and guardian angels, which do things we don't know how to do.
Often when you make a scientific discovery, you start laughing. And the reason is that the universe didn't change just because you saw something. It was already around us, and like a joke, you just couldn't see it.
To realize that these early ideas, data abstraction and specifications and programming languages and so forth, to understand that they had moved so into the mainstream that everybody knew them, and they were the basis of how you wrote programs. I mean, that was just a remarkable thing to understand.
But now, what I'm trying to do is distill off what I think is going to be of lasting interest. What parts of the things that people are doing today are people going to be interested in 50 years from now?
Today, we have all this tremendous amount of data out there, tremendous amount of connectivity, and there's a really pressing question. Now what?
So there are all kinds of concerns that people have about safety, about reliability of these devices, about their security, and whether or not they preserve privacy.
Everything we do is already known and knowable. I don't think we have any privacy at all.
This space of computing is exploding It touches so much of everything we do in all the sciences. Now every science is beholden to our ability to compute.
I'm Craig Partridge. And I'm Fahad Dogar. And we are delighted to serve as co-chairs for an outstanding ACM event in 2017. Next June, in memory of Alan Turing, ACM will celebrate 50 years of computing's greatest achievements in an exciting conference in San Francisco. We will feature many of the recipients of the Turing Award, as well as other leading researchers in computer science. We'll be exploring the evolution of computer science and where it is headed in a series of lively, moderated discussions in which the experts take questions from other experts as well as those attending. So please, plan now to join us either in person in San Francisco or on the web as we stream these sessions live. 50 years of celebrating computing's greatest achievements promises to be a truly unique experience. We look forward to welcoming you in San Francisco.
You can see that conference has already been completed in June, but still we chose to play the video just to get the awareness regarding the ACM Turing Award. And now, I would like to welcome all of you for this evening's talks on the contributions of the 1976 Turing laureates, Professor Diana Scott and Professor Michael Rabin. This is the third talk in the 50 Years of Turing Award series of lectures. Scott and Rabin received the Turing Award for coming up with the powerful concept of non-deterministic machines, which laid the foundation for the entire computational complexity theory. Professor Scott, along with Strachey, also did pioneering work on applications of logic and algebra to the development of mathematical semantics of programming languages, which has later come to known as denotational semantics. Rabin is also credited for one of the most well-known efficient primality testing algorithm, Rabin crypto system, and the famous Rabin Corp string search algorithm that makes use of the notion of a rolling hash. It's going to be an exciting evening hearing more about all this from a wonderful speaker, Professor R. Ramanujan. It's my great honor and pleasure to introduce him. He has been with Institute of Mathematical Sciences for more than 25 years. He is indisputably one of the most inspiring teachers in the country. The energy, enthusiasm, and passion he infuses into each and every one of his talks and lectures is legendary and unmatched. His research interests are mathematical and philosophical logic in computer science, security protocols, theory of distributed systems, and foundations of game theory. Apart from pursuing hardcore research in theoretical computer science, he has also been playing a pivotal role in motivating generations of school students through the numerous outreach programs organized by Tamil Nadu Science Forum as well as IMSC. Ladies and gentlemen, please join me in welcoming Professor R. Ramanujan. Thank you.
Is it on? So, thanks very much, Dr. Chitra, and for the invitation, and thanks to all of you for coming by. We have already had our tea, so I thought I was supposed to talk till 6 o'clock until the tea comes, so now I can stop anytime I want, I guess, so that's good. And this is in fact the advertisement for the next Turing Award lecture, which will be on Leslie Lamport. So can we shut this down and get my stuff? Yeah. Can't see anything in this. Ah, here it is. Okay. Yeah, so today's talk is on Rabin and Scott, and Chitra has already introduced the speakers to you. So, and this is Michael Rabin and Dana Scott, introduced non-deterministic machines by publishing their first paper, this paper, Finite Automata and Their Decision Problems. So this is the citation from the citation of ACM, ACM Turing Award. It's very unusual that it refers to a single paper. Usually Turing Award is for lifetime achievements, and here it talks about this particular paper, Finite Automata and Their Decision Problem, which introduced the idea of non-deterministic machines and which has proved to be an enormously valuable concept. Their classic paper has been a continuous source of inspiration for subsequent work in this field. And this is from 1976. And the topic has been a source of inspiration for computer scientists, theoretical computer science especially. Interestingly, this is the only piece of joint work by Rabin and Scott. Both were PhD students of Alonzo Church and Princeton. They were working on problems in mathematical logic in the 1950s. Rabin graduated in 1957, Scott in 1958. They never worked together when they were in Princeton. I don't know if they even discussed very much together. But both were logicians working on some very interesting problems. 1959, IBM conducted a summer workshop for young researchers, and Rabin and Scott both participated in it. Discussed finite state automata during this, and worked together and published this landmark paper. Rabin went on to work on probabilistic automata as well as automata and infinite trees. We'll refer to them a little bit later. Scott did a little bit of automata theory. He worked on what he called definite automata, but then moved on. In fact, he felt that this whole emphasis on finite state was misplaced, as he said. He liked the kind of thing that Eilenberg was doing with semigroups, but otherwise he felt automata theory was not looking at the right questions, interestingly. So what did automata theory look like in 1959 when Rabin and Scott were looking at these problems? It began with the 1943 study of artificial neural networks by Walter Pitts and Warren McCulloch. Pitts. Artificial neural networks are much older, and that's really what was thought of as automata theory at that time, theory of sequential machines or something. So there's some interesting work on neural networks. And Rabin and Scott, their contribution was to kind of move away from that. And they said, okay, it's better to think about a Turing machine-like model. And Turing machines had been around for a while, and there was a lot of work in recursion theory, especially in the 1950s. And Rabin and Scott introduced this idea of read-only Turing machines. So these are Turing machines which, read their tape, but they can only read and they can't write anything. And they wanted to study a machine that would non-deterministically consider several potential alternatives at each step of the program. So you think of a program that's executing some steps. And this was the time when everybody was working with sequential machines. So your program has some instruction to do, executes it, takes the next instruction, executes it, and so on. Now suddenly these people say that, okay, if you're doing that, we should also look at a possibility where the machine considers not one next step, but several possible next steps, and just picks one of them. And they thought of it as an abstract machine which would read an input symbol, basically read some input, and then replicate itself, make lots of copies of itself, and not fixed number, but just as many copies as needed, and each one would proceed along a computational path. right? So you have a computational path to follow. Each copy will follow one particular computational path. And they actually, this is the model that they set up and worked with in this paper. Why would they do something like this? Now, it doesn't seem like a very realistic thing to do, right? I mean, a machine that makes copies of itself, as many copies as needed, and then explore many paths in parallel. Why did people think this was an interesting thing at all? Okay, so one way to understand this is, okay, from the viewpoint of complexity theory, non-determinism is very important. What is this? So computational complexity theory is the study of what is possible to calculate given a specific set of resources. You have constraints, say time in terms of number of steps, memory available, etc. And so rather than focusing on a single algorithm and analyzing its requirements, you would want to consider several alternatives simultaneously, maybe guess one and verify it. So for instance, there may be different ways to carry out a search, and we might want to proceed without committing to one specific strategy. Simultaneously consider several search possibilities at the same time, right? So there are several possibilities that I want to consider at the same time and explore how the computation proceeds. So this is really the model that Rabin and Scott paper introduced, among many other things, in fact. But this was the central thing that singled out, so I'm discussing that. So non-deterministic machines provide for precisely such abstractions. And so this is the Google era, and search is a big part of life. So non-determinism is best understood as a kind of primitive instruction, search for X, right? It would be nice in your programs, you just say, I want to find X, search for X. If the search succeeds, pick up X, move on, right? And there is an important conceptual role in having an instruction like this, right? So what Rabin and Scott are telling you is introduce a primitive like this, right? Search for the X that you are looking for. And so the important conceptual role is in exposing the existence of a search step. In my algorithm, there is a particular search step like this, and having a non-deterministic move exposes the existence of such a step explicitly. Then you can ask a question about whether that search step can be eliminated or not. You can develop an algorithm assuming such a search succeeds and search for it, proceed, and then later worry about whether I can eliminate it or not. And this is all, of course, paraphrasing and reinterpreting Rabin and Scott. But in some sense, so they show that for these finite state devices, it can indeed be eliminated, but there is an exponential price to be paid. And this way of understanding things and the analysis that went with it inaugurated a whole lot of thinking along these lines. And this became very important for complexity theory too. So this is where I don't want to go on more into the particular paper and non-determinism and why non-determinism is considered as important, but this is to say that this is one of the seminal contributions, and the concept of non-determinism went on to inform much of complexity theory as we understand it today, and most of the important questions arise from that. We can come back to it a little later. So I want to talk from now more about different contributions of Rabin and different contributions of Scott, and why their work is considered so important in theoretical computer science, especially. And even saying that, I'm not going to even cover all that kind of things that Chitra mentioned in her introduction. So even choosing a subset is already big enough. So I want to emphasize that this is a very Wikipedia level talk. All the information that I'm talking about, in terms of the biography and of these people is all available on the internet. The Turing Award lectures are, every Turing Award in the site, you will find the award lecture is also there. The articles were published in Communications of the ACM, and you can see the articles, and these are very informative. There are also interviews with the awardees, and they're also worth listening to, where there's a lot of information available on the times when they were doing things and so on. So in the case of Rabin and Scott as well, I learned a lot from these interviews. There's a very nice biography of Alfred Tarski, and why Tarski is being mentioned here when I'm talking about Rabin and Scott, well, if you read the biography, you will know. But, Tarski in some sense influenced an enormous amount of mathematical logic in the mid-20th century, and Scott and Rabin were also deeply influenced by that. But so the Pfefferman's biography contains a lot of very interesting information that I found. Anyway, so I don't have much more to say on that. So this is Michael Rabin, and a short biography, born on September 1, 1931. So he's, almost 86 years old now, in what was Breslau, and now it's called Wrocław. Of course, I can't write it in the correct Polish spelling. And so within a few years, the family moved to Palestine, and he was taught mathematics by Elisha Netanyahu, who was a major influence. And if the name makes you sit up, it's for the right reason. So Elisha Netanyahu's nephew is the one who's being hugged very many times by Modi ji right now. So this is the uncle of the current prime minister, and he's a very interesting character in his own right. I mean, he was a school teacher, and apparently an excellent mathematics teacher who seems to have had very, very bright students as well. And then I think a lesson for all of us to take seriously. So he was a mathematics teacher who published some very good mathematics, went on to become a professor in University of Jerusalem, and retired as Dean of Faculty of Science. Okay. So, and as a school teacher as well as at the university, he inspired a few generations of students to do mathematics, and one of them is the one that I'm talking about here. But if you go and read, so I found that the life of Elisha Netanyahu is actually very, very interesting to read about, and I should thank Chitra for giving me this opportunity to read about people like him. Okay. So another interesting thing about Rabin is that, so like in Israel, everybody had to go through military service, and while doing military service, he taught himself set theory, which is also something very interesting. That if you are, and he says that he had to do these sentinel duties. So if you're spending hours and hours as a guard, doing sentry stuff, walking around and sitting around, what do? You learn set theory, right? So, and so he became very good at Zermelo Fraenkel set theory, and it so happened that Abraham Fraenkel was in Jerusalem. So he wrote to him with some doubts, and Fraenkel realized that this was a very bright student. So in fact, he pulled him out of military service and invited him to the University of Jerusalem, where Rabin went on to do master's degree. So his master's thesis solved an open problem posed by Emmy Noether, and on the strength of that, Church invited him to, he applied to Princeton and got a position with Alonzo Church for a PhD in Princeton, and he did a PhD thesis on unsolvability of group theoretical problems, which is itself another very, very beautiful piece of work. So, and as I said earlier, he graduated in 1957. So as I've already mentioned, he graduated in 1957, and then he was hanging around in Princeton, I must say, because he was there for a year, he was there in Stanford for a year, and somehow he landed up in New York, and then he was in IBM. IBM invited him for this thing in 1959 when he wrote this paper with Diana Scott, and almost immediately, another year he was there, and then he went to Jerusalem. And so almost soon after he went to Jerusalem, and then he returned for the IBM summer workshop, and this time he met John McCarthy, who was famous for posing puzzles to a lot of people. Actually, McCarthy's, one of his well-known contributions is finding all kinds of amazing puzzles and getting people to think about them. And this was one of his puzzles. So he posed this problem. So there are two kinds of people, spies and guards, all military stuff. And the spies go out, infiltrate the enemy and come back. And so they have passwords that allow them to go from enemy territory to their own. I suppose for somebody coming from Jerusalem, this was all, immediate and important. Yeah? And then, so the guards need to know the passwords to allow them in, right? And these guys are coming back. But it turns out that the guards cannot be trusted to keep the password secret. So you need to find a method to verify that even if the enemy gains knowledge of the password, the spies can safely return, but the enemy infiltrators are kept out, right? So some guards may leak some information, so the enemy could get hold of whatever information that the guards have. So you want to come up with a system by which the spies can return and the guards can verify that these guys are decent, but the enemy infiltrators are kept out. And apparently this had been floating around and was being discussed by various people. And one of the persons who heard about it was von Neumann, and he gave a solution. And this is what is now called the middle square method. And he, anyway, was using this to generate random numbers. But anyway, so this is von Neumann's solution. Each spy is given a 100-digit number, x. The guards are given another 100-digit number obtained by taking so you take x squared and take the middle digits. And this is all that is given to the guards. Okay? So the spies get x, and the guards get the middle digits of x squared. So now when returning, the spy gives the guard x, and the guard then computes x squared and compares the middle digits to the number he possesses as a passcode. And there is some, I'm paraphrasing, there is some minor difference here. So even if the guard passes his number to the enemy, it is very difficult for the enemy to determine the original number x that resulted in these 100 middle digits of x squared. So this is the idea. And and this was passing around, and it was something discussed by McCarthy, and Rabin heard about it, and this got him really thinking quite seriously. And they were all looking at variants of the problem and trying to come up with different schemes. And this was really, as I said, the thing passing around in Stanford at that time. But Rabin had a very interesting take on it. He didn't look for variants or their solutions at all. He was really intrigued by the middle square method. He said, okay, of course it's not impossible to find x knowing the middle digits of x squared, but it's certainly difficult. But difficult for whom? How do you prove that something like this is difficult, right? So while all the others in Stanford were thinking about different schemes for different variants of the problem and doing all these things, Rabin took up a very different task. How do I define that finding the middle digits is difficult? In general, how do I show that a function, computing a function value is difficult in what sense? Remember, this is 1960. Today in computer science, we use a lot of stuff about polynomial time, reductions, NP, etc. But in 1960, he was sitting and thinking about it. And he wanted to quantify this idea of difficult to invert, right? Where it's not impossible, the inverse exists, but difficult to compute. And he wrote a paper called Degree of Difficulty of Computing a Function and a Partial Ordering of Recursive Sets. So it's a groundbreaking paper, which is a starting point of later advances in the study of complexity in relation to cryptography. I know that I must see that a lot of people, our students know complexity theory very well, but I would still think that this paper has got a lot of, it's very likely that there will be some new thing that you will learn reading this paper, because it really goes back to fundamentals, It's, from first principles, takes up the problem of how you would define, and, and he's thinking in terms of recursive functions and recursive sets and coming up with a really beautiful definition. Of course, there's been a lot of movement since then, and Rabin himself has contributed extensively to this relation between complexity and cryptography, but in some sense, this paper launches this very important connection, which has become very important for us to use PGP and SSH and remote logins, all these things that we do today. So in some sense, Rabin is grasping with the fundamental nature of the problem that is involved. Okay, so he was in Jerusalem, I think, for a number of years after that, and he again visited MIT in 1975. There is one more visit in between that I'm missing. In fact, each time there's something about sabbaticals and visits, I guess, right? Because Rabin wrote a lot of papers, but each visit to the US, I think 1969 is another famous one when he worked on probabilistic automata. I am skipping that. And 1975, he visited MIT, and he met Gary Miller. And each of his visits has, launched some particular area of computer science as we know it today. So Miller had devised an algorithm to check if a given number was prime, and assuming the Riemann hypothesis, something familiar to mathematicians, but. And Rabin had earlier worked on probabilistic automata. Now, it's basically automata, but where it's not a non-deterministic step. There are several alternatives to be considered. You flip a coin and decide, okay, with probability half to go this side, or you can think of it that way. So, in general, a random number is used to determine which transition to take from each state. And he decided to approach the same problem, but using probabilistic automata. Again, today the presentation is different, but this is really how he got to it. And he came up with a primality testing algorithm. And this is a very important and very different idea. And so this is not it doesn't rely on any hypothesis, very elementary, a simple thing. Today we call it the Rabin-Miller test, or Miller-Rabin, whatever. And so primality testing algorithm. And so adding randomness, so this started off a very important line of research for Rabin. This algorithm itself is something very interesting, but adding randomness to algorithms became a theme in much of Rabin's later work, especially in distributed computing and cryptography. And he had lots of things to say. I don't know if I have. Yeah, so I wanted to also remark here that apparently he met a lot of hostility. Remember, he was a mathematician, right, in Jerusalem, and most mathematicians he met didn't like this idea of trading certainty for speed. I mean, right? So you're giving a probabilistic answer. I mean, come on. I mean, you're saying this number is prime with a very high probability. What is this? I mean, the number is prime or not? And I want to know whether it's prime or not. What is all this saying that? So this, apparently, it's also heartening for people to realize that Rabin had apparently major difficulty publishing this paper first. So it's in the interview, it's very nice because he says, first time I submitted the paper, it was rejected, and a referee had, this is a quotation from the review, if he had attached a pen to his dog's tail, he would have proved Riemann hypothesis with positive probability. I don't know where this dog's tail comes, but yeah. So he got some nasty reviews and so on. If you hear the interview, he says many things about initially the kind of resistance that was there. And remember that we are talking about a time, this is not computer science departments, didn't exist, right? He was a mathematician and working on mathematical problems. That's how he thought about this whole business, right? And most of the problems that Rabin worked on are all algebraic problems, arithmetical problems, things of that kind. So he never saw himself as doing anything else at that time, anyway. So this is something that he had to overcome. And he was saying, as a community, we had to face some questions on this. another quote I liked from the interview is the probability of, so he was trying to communicate in talks and lectures that the probability is very small. But what does that mean, right? So anyway, so he was, in one of the lectures, he says the probability of an error is smaller than the probability that none of us is awake and we are all dreaming this whole theorem. In later years, so this is, as I said, he went on to do a lot of work on randomization and randomized algorithms, but there's a very interesting quote from him. I must admit that after many years of work in this area, the efficacy of randomness for so many algorithmic problems is absolutely mysterious to me. It is efficient, it works, but why and how is absolutely mysterious. And he considers explaining why randomized algorithms are very simple as one of the very important problems for theoretical computer science to take seriously and study. And in fact, he says this is a problem that a logician must explain as to why is it that randomized algorithms are so effective in so many areas of computer science. And again, this is something that now theoretical computer scientists know. So many places where there are all kinds of clunky algorithms around. Randomized algorithms are very simple, 4 lines, and works beautifully. Analysis may take several pages, but the algorithms are very simple. And so what is going on? There must be a good mathematical reason. And he says the logician has to explain this. Anyway, so this is a more recent remark. My favorite of Rabin is this problem from operating systems of all things. And this is a paradigm problem due to Dijkstra called the dining philosopher's problem, and to illustrate the difficulty of coordination in distributed systems. So for those who have never heard about it, it may be, it'll take some time to explain perhaps, but you can think of, n philosophers sitting around a circular table, and there is a bowl of spaghetti in the middle, and you need 2 forks for some reason to pick up spaghetti. So there is 1 fork on each side. So every philosopher I has a fork to the right and to the left. Now, philosophers, what do? They think, and then they suddenly feel hungry, they eat some spaghetti, and then go back to thinking. But to eat, when you're hungry, you need 2 forks, right? Which is no problem. But if at that moment the philosopher to my right was also hungry, that fork is gone, right? Sorry? Right. It's not that I have 1 fork to myself, but everybody has exactly 1 fork to the right and 1 fork to the left. So of course the middle fork is shared by 2. So the trouble is that at the same time, so maybe I can pick up my left fork, right is not free, and wait for it to. So the person to my left is then therefore deprived, right? Because I'm holding on to this fork. Maybe I put it down, and then the person to my left picks it up, and that's exactly when the person to my right is putting it down. So it's a bit of a pain, right? So, and then you have to consider a situation where symmetrically everybody picks up the right fork, and realizing that it's not going to work, puts it down, and everybody picks up the left fork. So all kinds of problems are there. So Dijkstra used this story to illustrate problems of coordination, and he went on to analyze these things in a very nice way. Now, there is a paper in 1980 by Gabay, Pnoeli, Shela, and Stavi, which showed that there is no symmetric, deterministic, fair, and distributed solution to the DPP. And this is, again, I'm putting it down for those who know logic to show that these are all like famous names in logic, logicians who were trying to do these. And unfortunately, I shouldn't have written it this way. So, because the claim that that paper actually has is there is no symmetric, fair, and distributed solution to the DPP. So next year, Neumann and Rabin gave an extremely simple and beautiful randomized algorithm for DPP that is symmetric, fair, and distributed. And the main point was that, as I said, it was my spoiler there. The GPS's result only says there is no symmetric, fair, and distributed solution to the DPP, because they were only considering deterministic solutions. It never even occurred to them to put it as an adjective. I did the stupid thing because this is how I remember the theorem and I wrote it, right? So, and this was the point that Neumann and Rabin established, that here is a theorem that says there is no symmetric, fair, and distributed solution to the DPP. Here we give you one, because you guys are thinking only deterministically. The moment you think in a randomized fashion, here is a solution. And it's a very simple randomized algorithm. It says that, okay, at any point of time, if you are hungry, well, you decide which fork you're going to, which side you're going to look. Am I going to look to my left or to my right with probability half? And then, having looked, if it's available, I decide whether to pick it up or wait with probability half. And that's it. And they show that, then it's completely symmetric, everything works beautifully. Yeah, so they show a counterexample to show that both steps are needed. No. To look, to examine, you do with probability half. That is the first step. Having looked, if it's available, to pick it up or to wait. And supposing you don't do that, right? I mean, you have only one, then they do a very complicated scenario where things go wrong. So anyway, so this is this was the launch of a whole lot of randomized algorithms in the world of distributed computing. And I want to mention that because today, routing algorithms and on internet, most of these things are randomized algorithms. Right? And internet technology heavily uses all these things. Switching networks use randomization at the core. You will find many times that you're trying to reach a page, right? And it takes forever to load. You shut it and then try again, it comes very fast. What is that? It's all because of randomization. Everything is randomized in these things. Switching, same thing happens in telephone networks. Now, today it's all built into everything, so we take it for granted. But this, in 1981, when Neumann and Rabin proposed it for distributed computing, it was quite a revolutionary idea. The way the speed of these things is such that, of course, within 20 years it became the norm. I don't think anyone even thought about questioning what. But initially people said, what is all this nonsense? You want correctness guarantees, you want these things. How can you, gamble with correctness? I remember, discussions which raise issues like this. You want your systems to be correct. How can you gamble with such things? Anyway, so Rabin went on to do a lot of very interesting work in this thing, so let me not go on. I want to mention, even though this is not the sort of stuff in the Turing Award, Rabin made many fundamental contributions to logic. Perhaps the most significant of them for computer science is the Rabin tree theorem. Just very quickly, I want to mention what that is, because it's a really deep theorem. Gödel showed that the first order theory of arithmetic with addition and multiplication is undecidable. I'm sorry, I've written decidable. It's undecidable. This is the remarkable result of Gödel in 1931. And then various people showed various things. One of the things that there is a question about, okay, you're talking about addition and multiplication, the same thing that Tarski looked at over the reals and showed it to be decidable. But then with arithmetic, just with addition, it was decidable. That was shown by Pressburger. So addition and multiplication is bad. Okay, what if I look at something weaker than addition? Tarski asked the question, if you just look at the theory of order, is it decidable? Can I go over to stronger theories like monadic second order theories? And this was shown by Buchy that in fact it is decidable, and he used automata theory to solve the problem. And that is a very interesting result in itself. But then Rabin came along and extended the techniques to show that, arithmetic you think of as the theory of linear orders, where every element has a single successor, discrete linear order. If you want to look at the same theory with multiple successors, let's say 2 successors, what happens? And then you get the infinite binary tree. And Rabin showed that automata theoretic techniques can be used to show the decidability of the theory of the infinite binary tree. And he went on to show that it's not binary branching, finitely branching. You can also look at omega branching trees, and these theories continue to be decidable. But the techniques he used of automata that run on trees, run on infinite trees, is something that turned out to be extremely important. And the consensus today is that in a kind of deep sense, it represents the the boundary of such decidability in such theories. In the sense that first-order theories over linear orders have certain properties, and the moment you go over to graphs or partial orders, almost everything is undecidable. Trees are decidable, and the only kind of structures that are decidable are those that have interpretations in tree theories. No, this is a 30-second explanation of this. Graphs are kind of hard, trees are kind of easy, and Rabin showed a way by which you could also, get tree interpretations and get algorithms. And Rabin himself says that I consider this the most difficult research I've ever done. And that proof, which we usually now present in many of our logic courses, is really a tour de force. Wolfgang Thomas, to quote, says a fundamental decidability result that appears in hundreds of applications in theoretical computer science. Today, we take browsers for granted, operating systems for granted. These are all non-terminating programs. These are not algorithms that stop and give a particular yes or no answer or some output. They are just the computations are infinite, right? I mean, a browser or a browser is a good example. It's just sitting there. You can think of it as a reactor system. It just takes inputs and produces outputs. And it just goes on forever, Infinite non-deterministic computation infinite state computation is something that we take for granted. Analyzing such things is possible. One of the principal tools that, you need in this is the Rabin tree theorem. Okay. Last remark on Rabin. I have already spent too much time on him, which is, where he says there is this misconception that there is a conflict and maybe even a contradiction between great teaching and being able to do great science. I think this is completely incorrect, and that wonderful teaching flows from a deep understanding of the subject matter. So he has written extensively about teachers and research and so on, and therefore I wanted to mention this so that you can go and, if you're interested, you can go and look at his articles. Most of them written in Hebrew and translated in English, available on the net. So this is Dana Scott, and this is the Vienna Summer of Logic 2014, when he gave the inaugural lecture. A very short bio. Was born in a year after Rabin in Berkeley, California. And he did his undergraduate studies in Berkeley. Tarski was a major influence for him. And he learned the lambda calculus of Church, which he said literally gave me nightmares at first. And so he went on to do a PhD, again with Alonzo Church in Princeton. And he worked on theories of measurement. That's his PhD thesis. And after his PhD, he continued to work in Princeton. He was working on the continuum hypothesis. And, I've already said that he graduated in 1958 and met Rabin in the IBM workshop in 1959 when they wrote this paper on non-deterministic automata, or non-determinism in automata. And, he was in Chicago for a few years, and then he spent a couple of years in Amsterdam. He met Christopher Strachey, this English mathematician, and he started work on semantics of programming languages. He moved to Oxford, spent a number of years in Oxford, which is when he developed the denotational semantics that Chitra referred to in the introduction. And then by 1989, he moved to CMU, which is where he was until he retired a few years ago. So Scott worked on what he called a mathematical theory of computation. Rather interestingly, Strachey himself didn't know about the lambda calculus, and it was Roger Penrose who introduced lambda calculus to him, and as a functional abstraction for programs. So lambda calculus is a programming notation that was advanced by Alonzo Church. Independently of Turing, he came up with the notion of effective procedure, and today you can think of it as an abstract programming notation for talking about functions, which takes functions as arguments, and that's basically it. And so Church showed that anything that is computable is definable in the lambda calculus. Turing showed that anything that's intuitively computable is computable by a Turing machine, and Turing and one of Turing's early work was to show that lambda definable functions are exactly the Turing computable functions. And there is a lot of work on lambda calculus that is going on, but at the level of syntax there is a lot, but understanding exactly what's going on, the meaning of denotations of lambda terms was a big question. And this is the kind of status it was. And this was 1960s, late 60s, 1968 in fact, when he met Strachey. There was this programming language called Algol. Algol 60, Algol 68 was being developed. And in fact, the first meeting was during IFIP working group. There was this International Federation for Information Processing, which was trying to define how programming languages should be. And Algol 68 was a major exercise that was taken up. And Scott says that when he went there, he was impressed by how much fighting that was going on. People were like bitterly, shouting at each other, and my language is better than yours, kind of stuff that was going on. And he was very impressed. I mean, he felt that Strachey was one of the more sensible persons among the lot, though he was also fighting. But by then, okay, there was a different problem, which I'll refer to later. Okay, so he was also looking to get out of Amsterdam, and Strachey, kind of was talking lambda calculus as a way of talking about programming languages, and Scott remembered the kind of nightmares he had had, and so he was not very keen on lambda calculus himself, but there must be a better logic, he was thinking. But soon he got into this question, and he asked a very important question. This is almost the same thing like I said with Rabin and that puzzle, right? While all these people were doing something, he asked a completely different question. Same thing happened with Dennis Scott. At some point, it didn't matter to him what these programming languages were about, but he really asked, what are the spaces that computable functions live in? Okay, so whatever programming language you write your program in, abstractly the program is computing some function. It's an element of some function space. What is that function space? What are the mathematical characteristics of this function space? So without doing that, how can my theory of computation be mathematical? So that's really how he says. I wanted to build a mathematical theory of computation, not something that just, and it's very ironical that he says, what is all this automata business with states and transitions and so on? It's okay, I can live with all that, but I want to know what functions do they compute. Well, I know that this is all the computable functions because that is the space in which we are in. But what are these spaces that they live in? And the trouble with programs is that there is no difference between programs and the data that they operate on. Functions can take functions as arguments, and recursive functions call themselves. What is this call, right? And how do I really represent this? The operational meaning of a program, I look at the program, I can think of it as given by some machine. The way the machine will execute it, right? The machine will be in this state, and then this instruction is executed, it moves to the new. So I can describe the operational meaning of what is going on in a kind of phenomenological way. I have this program, I go take it to a compiler, I do something, the machine will go through some state and state transitions, right? So I can describe it in that way. But that doesn't help me. I want to know what is this function that it's computing. So I should think of the meaning of the program in terms of, I don't care about it's assigning something, it's changing storage, updating a pointer, it's doing all that, but finally it's computing some function in some space. What is that meaning? So this is the denotational meaning. What is this? And Scott proved an important theorem where the statement is the computable functions on a space D are exactly the continuous functions over D, over in a suitable topology. And that is the main theorem of Dennis Scott in semantics. So he showed a solution to the equation f is isomorphic to this f arrow f, which consists of continuous functions from f to f. So basically, if you want to talk about functions that take functions as parameters and can call functions, I need a function space which is isomorphic to the space of functions from F to F, the space of continuous functions from F to F. So you set up an equation like this and solve. And his main insight was that if you can give a semantics to all this lambda calculus, what Church had already shown that all computable functions can be defined in the lambda calculus. So if I can show that lambda definable functions are exactly the continuous functions, then for the syntax that lambda calculus represents, I have the right semantics. And this he went on to do. And this is a kind of tour de force and lays the foundation for giving a formal semantics to full programming languages with rich features. So Scott took it up for a very simple mathematical notation of a programming language where you have some abstract basic operations and recursion. Recursion is the big deal, right? And that's the main thing that you can do. You take a function, apply it to arguments which can be functions. And in general, given anything, take an argument, I can abstract it out as a function. That's all that lambda calculus is, and he gave a model for that. But today, now you can follow that style and give mathematical semantics for C programs or C++ or D or whatever you've got. You know, it's a matter of setting up domain equations of the appropriate kind and solving them. It's not very easy. Oh, I'm sorry. There's a fair amount of mathematical work involved, but I must say that the main mathematical question was really solved by Scott. After that, it's all imitation and working out particular things for a particular programming language. And today, you know, I think maybe with the exception of heaps are, I think, still a bit of a challenge. I think dynamic data structures, whatever kind of object-oriented, whatever you can think of, you can do a mathematical semantics of this kind. And Scott, what is, I think, very important for me, I would say that in the process, Scott gave us notions of approximations, limits, projections, and other tools similar to that of mathematical analysis. So that, and his point was that analysis starts with numbers, right? I mean, analysis, I mean real analysis or complex analysis. And in mathematics, analysis proceeds in a certain way. It starts with functions. The critical thing is this notion of approximations, notion of limits, and then continuity. Once you have this, you can build up analysis. I should be able to do the same thing with programs as my objects. I want to take functions, programs as objects, define a notion of functions in such a way that I can talk about notion of approximations, limits, and continuity, then I'm in business, right? So I should, we set up a differential equation, and that says here is a process. The differential equation describes what happens for all time, right? This is supposed to be the idea. And I give initial conditions, and this describes. I should be able to do that with program. You take a program, I should be able to give an expression that describes what will happen for all time, its execution, whatever you can say, right? And this is, as I said, is a real tour de force. And Scott's dream is program analysis should achieve the sophistication of calculus. I'm afraid it's still a dream, right? Program analysis is extremely primitive compared to the kind of sophistication that, you know, calculus has. Calculus, you know, we harass our 15-year-olds to learn derivatives and integration by parts and so on. But the idea that you don't really need to know deep analysis. You know, you can learn certain techniques, certain tricks, and then you can actually go and do, you know, engineering, build technology, and it'll all work. So huge amount of, so you're able to bring it down to calculus as just certain things that some things that machines can do, some things that human beings can do. You don't worry about getting analytical solutions for everything. But you know, people can actually do. So he wanted to do something like that with programs. But that, as I said, is. So there are notions like differentiation, integration, and so on in programming theory as well. But they are, I would say, esoteric. So a very quick intro. I'm not going to take very long, just 5 minutes. So consider a program outputting a stream of numbers. I don't know what it's doing. Initially, we know nothing about what it does. Denote this by the symbol bottom to say, I have no information about the program. After a while, it puts a number in 1. And we have a little more information than what we had initially. From no information to say that, it can output in 1. Proceeding further, you can think of a stream like it starts and then produces N1, N2, N1, N2, N3, and so on, and maybe it terminates after Nk. Now, in this notation, that sequence N1 to Nk means it's a partial stream, something may come later. The little bracket to say, no, it's died after that. What if it never stops and produces an infinite stream? That's a complete output as well. Infinite streams that are least upper bounds of finite streams are the kind of limits in this information ordering. So there is a kind of information ordering. So you work with some bottom element and you climb up. You can maybe a lattice. And up there are infinite elements with finite approximations. This is the kind of structures that he worked with. So the important point is that for your program, if your program is computing a function, then that function, the output should be determined only by a finite part of the input. This is the main idea. So if the input to a program is a stream approximated, V0, V1, V2, etc., your program can only produce, it can't go back and erase part of the input, right? So it's monotone in some sense, that it gives successive approximations of the output. As it, think of an operating system, right? It keeps on getting a sequence of requests and it keeps on doing something. So at every time, it's approximating its eventual output. And a function computed by P should map the limit of the inputs to the limit of the approximations that it has produced. So basically, it should preserve limits. This is the idea of continuity. And, intuitively, discontinuous functions need infinite amount of information from the input and hence are not computable. So this is a 30-second introduction to Scott's theorem. But there is a lot more there. Okay, so I don't want to say more. I don't have much time also now. So Dana Scott is one of the most influential logicians of the last half century. He has done an enormous amount of path-breaking work in mathematical logic. And even writing a few things like this in one slide, I realized, it's very difficult to talk about contributions of Dana Scott. Because infinitary logic, I know, this is again, a very remarkable idea. Instead of talking about, when you think of a disjunction A or B, conjunction A and B, right? Why should we think of finitary conjunctions and finitary disjunctions? Why not look at infinite disjunctions and infinite conjunctions? And Scott developed a theory of that, and then he showed that many other logics that logicians are thinking of can be embedded into some infinitary logic. And by choosing the kind of indexing over sets that you are working with, you can control, get different results, and build a general kind of recursion theory based on that. 30-second remark on Scott's work in infinitary logic. Then he worked on Boolean valued models of set theory. This is another very important thing, where he gave an alternative proof of the independence of the continuum hypothesis. Cohen had proved this remarkable result in 1964, and at the time people couldn't understand Cohen's proof. And Scott came up with, he developed this whole idea of Boolean valued models of set theory, following a suggestion of Soloway that led to some problem. Because Soloway independently wrote a separate paper, and then he said, oh, Scott stole my idea, and so on. Anyway. And so Boolean valued models of set theory, he developed the whole technology so that he could give a neat and highly structured proof of Cohen's result. And I think today most proofs, there are two things that you will find repeatedly coming up: forcing, which is an idea that Cohen had, and Boolean valued models. And anyway, so for people who want to look at esoteric stuff in set theory, these give very nice pathway to get into. And then there is Scott's trick, as it's known. I like that very much because one of the big questions that was there since von Neumann defined ordinals and then later went on to define cardinals in set theory, there is a nice development that von Neumann set up, but cardinality is defined using bijections, which requires equivalence, and that requires axiom of choice. And there was a question that von Neumann left open, asking, is it possible to define of some, I would say the analogy would be the Weierstrass kind of cleaning up of analysis. So a lot of very interesting things happening, but no good coherent theory. So
No, the static analysis you are talking about or dynamic analysis? Which analysis is program analysis is this?
This 10-year stuff that I'm talking about, a combination of all of them.
Scott's dream. Is it static
so
analysis?
Data flow analysis goes back to Fortran. Okay, data flow analysis is as old as Fortran, right? The very first Fortran compilers, Fortran 4 compiler already had a lot of optimization, data flow analysis and so on. But in the 1980s, after Scott, people started looking at more sophisticated analysis. And today, the kind of things that I'm talking about in the last 15 years combine all these things and more. And in fact, they combine these techniques as well as linear programming, optimization theory. So, but as I said, it's all very ad hoc. I mean, we don't know. Putting it all into one nice mathematical framework is very far. But these are very impressive things that are happening. Backtracking algorithm, okay. So think of it as a search, there is a tree, right? I'm going down and looking for a solution which is somewhere there. But the tree is very large, right? So now, in general, if I go down a path and find that what I'm looking for is not there, I have to go up and then try another path, right? Now, do I locally do everything and then come up, or jump far enough and then do? That's a backtracking question. It's a non-trivial question to solve. Okay, thank you very much. And thanks for staying here.
On behalf of Chennai chapter, I would like to thank Professor Ramanujam, and I would ask the Chennai chapter chair, Professor Rajesh Kumar, to hand over the memento to Professor Ramanujam.